then we have no limit for our function f of x. Is it clear?
Yes, Professor.
Yes, very good. So as for this function sinus 1 over x, so the idea, you know that the classical example of a sequence which has no limit is the sequence minus 1 to the power n. I hope you know this. Yes?
Yes, we understand.
So, the idea. I show you the graph of my function sinus x. I think you have to know the graph of this function, but at least for this function, I show you if I take a point pi over 2, then my function is 1. Then if I take the point 3 pi over 2, my function is minus 1, and so on. So we hope that if we take the corresponding values of my sequence x n due to this graph of my sinus x, then I will obtain that there will be no limit for the sequence f of x sub n. In fact, you see, if I take here 1 x sub n as pi over 2 plus pi n, where n is a natural number, if you want. You see, then x sub n will be 1 over pi over 2 plus pi n. So we are looking for the limit at the point 0. So the first step, if you want, is that x sub n goes to 0 as n goes to infinity. Agree?
Yes, I agree.
Agree. Very good. So you see, in this case, the result now is very simple. The result now is very simple because I have to take the sequence of the values of my function f of xn, and it will be sinus of pi over 2 plus pi n. Now, I think that you know that the sinus of alpha plus beta will be sinus alpha cos beta plus sinus beta cos alpha. You know this formula, Eric?
Yes, I understand it.
Yes. So if you calculate your sinus of pi over 2 plus pi n, you will obtain minus 1 to the power n. Then we know that the sequence minus 1 to the power n has no limit. So the sequence f of xn has no limit, and it is the desired result of our exercise. Question. Eric.
No questions for now.
No question.
This is the sequence for infinitive, yeah?
You see, your sequence xn is defined as 2 over pi plus 2 pi multiplied by n. You see, as n goes to infinity, evidently xn goes to 0. Valentina.
Yes, I got it.
So for you, as a home task, for all the people, if you want. So please show me that the function cosinus of 1 over x has no limit at the point x 0 equals 0. Understand? You understand this, the question?
Yes, cosines
Cosinus
1 over
x has no limit at 0. As the sinus of 1 over x has no limit, so the idea for this home task is to specify the sequence x sub n, which gives us the desired result. Valentina, is clear?
Yeah, it's clear.
Good. Now we have another example which is very famous for the Russian students here in MIPT. So the so-called Dirichlet function. This function is given by the formula 1.3, you see, and this function is 1 if x is a rational number and 0 if x is an irrational number. So you see, as for this function, I can give you the graph of this function, but you can also find this graph on the web. It is not very complicated. So the exercise is as follows. We have to show that for any point P from the real axis, this function capital D does not have the limit. Is it clear? Is it clear, the exercise? The limit does not exist, as I have written here. So no limit for any point, for any real point P. Okay?
For me, it's not clear. You can explain again?
Yes, Valentina. You see, you have a real axis. Okay? Then you take any point P from this real axis. So for any P from capital R, we claim, you claim that if I take the limit as x goes to this point P of my function, of my Dirichlet function, there is no limit. The limit does not exist. You understand the question?
Yeah. Now I got it.
Thank you. So let us take any P from the real axis, and we have and we choose two sequences xn and x prime n converging, which converge to this point P. But we choose these two sequences in a following way. The first one, we take only for xn, we take only rational numbers. And for xn prime, we take only irrational numbers. You see, it is possible you have to know this from your lectures. So no comments. If you want, I don't know, do you know this term? The rational numbers are dense in the real numbers. So for any irrational number, we can find a sequence which converges to this irrational number. So if I take such two sequences and we take into account the definition of our Dirichlet function, we see that for the sequence xn, the values, the sequence of f of xn goes to 1, and the sequence of f xn prime goes to 0. Then due to our remark, this one, due to our remark, we have that for any point p from the real axis, for any real p, the limit as x goes to p of capital D of x does not exist. Clear?
Yes, it's clear for me.
Yes, Professor.
So maybe here, as for the last line, I write lim as x goes to p. Here I have to replace f by capital D, but here we have, I think, no problem, because here I write f of xn, f of xn prime. If you want, I will correct this. I will replace f by capital D. Clear? Hussein, is it clear?
Yes, Professor, it's clear for me.
Thank you.
Mhm.
So if you want, I will change f by, but the idea was to show you as in this remark, to show you the proof as in this remark. Okay, I will change this. Maybe it will be better. Now we will consider the so-called one-sided limits. So the definition is here, and I write that I take an open interval containing some point t, and I have a function f which is defined on this interval, except possibly at this point c. So the limit of f as x approaches c as x goes to c from the left, you see, is capital L, or the so-called left-hand limit of f as c at C is L. And we write, you see, lim x goes to C minus, or you can find in the literature also the notation like this, x goes to C minus 0. A very strange notation maybe for you, but this means that we take exactly the left-hand limit. So in the quantifiers, how we write this? For any epsilon, there is delta, which depends on epsilon positive, such that for all x less than C, we have, what do we have? We have that if C minus x is less than delta and greater than 0, then the absolute value of f of x minus L is less than epsilon. You see, it is maybe you can compare this definition with the definition of the usual limit at the point C. So here you see you have that C minus x is less than delta, but in the usual definition you have the absolute value between of the difference C minus x, which have to be less than delta. But now, and limit, you have that x is less than C. So I rewrite this absolute value in the following way. Is it clear? Or it is necessary to show the initial definition of the limit?
Yes, it's clear.
That's okay. I mean, I'm not.
Thank you. Clear?
Yes, Professor, it's clear.
Good. So in the same way, we can define the right-hand limit. So as in the previous definition, we have capital I, which is an open containing defined on this interval, except maybe this point C. Then we can define the right-hand limit of f, and this limit is denoted by capital L by this. Is not the formula, but if you want, it is a notation. In the quantifiers, this right-hand limit is defined as follows. So for any epsilon, we can find delta, which depends on this epsilon, such that for all x greater than C and x minus C is between 0 and delta, and this implies that the absolute value of f of x minus capital L is less than epsilon. It is this similar thing, you see, as for the right-hand limit, we have all our x which are less than C. For right-hand limit, we have all x which are greater than C. Agree? Is it clear?
Yes, sir, it's understandable.
Understandable. Very good. So now, as for the usual limit, you see, there is a theorem, maybe you know this theorem from your lectures, but I want to recall you this theorem that a function has a limit at a point C, if and only if the left hand and the right hand limits exist, and they are equal. Okay. So I write here that the limit as x goes to C of f of x is, if you want, f of C minus equals f of C minus 0 equals f of C plus equals f of C plus 0. So the left hand side, the left hand and the right hand limits coincide, exist and coincide. They are equal. Agree? Do you know this theorem from your lectures?
Yes, I agree.
Yeah, we know that
You
term.
say,
Mhm.
very good. Very, very good. So now, you see two exercises on the subject. We define my function, our function f of x by the following formula. By the formula like this. So it will be x if x is between 0 and 1. So this function is defined for all x which are greater than or equal 0. We include 0 in our interval, and less than or equal 1. The second line here, my function is 3 minus x is if x is between 1 and 2. We exclude in this case the points 1 and 2. So before formulating the questions, I will show you the graph of my function. You see the points in black are included, and the points in white are excluded. So if you want, for example, the first part of the graph, you have that this point 0 belongs to your function, to the interval where your function is defined. This point 1 is also included, but there is no value for the second part of your graph at the point 1. So there is an only one point, this one, which is given by the definition of our function. Is it clear, or maybe I have to use some other words to explain you?
I think it's clear.
Clear. Good. So we have 4 questions. The first question is, find the left hand limit at 1 and the right hand limit at 1. So we go to our solution. Here we can say that, taking into account the graph of our function, maybe It is not a usual thing, but in this situation, maybe it is better to use the graph than the formal formulation of the formal definition, excuse me, of my function. So, question 1. As x goes to 1 from the left, then we see that the function, the sequence f of x approaching the value of 1. So the left hand limit of x is 1. You see, our left hand limit, we are going from some point to 1, you see. So we approach the value of my function from the left. And I know that this value is 1. So the left hand limit of my function is 1. Agree?
Yes, agree.
Yeah. Yes.
The same thing, you see. Now, we have, as for the point 1, x equals 1, this is the point of discontinuity of our function f of x. So you see that if we approach 1 from the right, I will show like this. If we approach 1 from the right, then you see the values of my function, approach 2. Agree?
Yes, I agree.
Yes, I agree.
Yeah,
Agree.
yeah.
Very good. So you see that in this case, the right hand limit will be 2. The left hand is 1, and the right hand limit is 2. At least you can say that there is no limit for the function f of x as x goes to 1. So it is, in fact, question number 2. We want to find the limit of f of x as x goes to 1 and the value of my function f at the point 1. Question 2. So you see, question 2, we have that the left hand limit and the right hand limit are different, so there is no limit. The answer is there is no limit for the function f as x goes to 1. From the other hand, you see, by the definition, I know that my function f of x is x when x in particular equals 1. So if you take your graph, you see that if I take f of 1, it will be 1. Agree? Agree?
Yes, I agree.
Valentina,
Yes, we agree.
clear? Hussein, clear?
Yes, Professor, clear.
Thank you. So now we have the third question. We have to find the limit as x goes to 0 from the right and f of 0. So you see, we go 2x equals 0 from the right. The limit evidently exists, and this limit will be the same to your mind.
Yes, Professor, what?
So the limit as x goes to 0 plus of f of x. This limit will be.
But there isn't exist in the left hand.
Yes, but you see, Valentina, I asked only about the limit, the right hand limit. You see, the left hand limit does not exist because our function is not defined for negative x. But as for the right hand limit, what can you say?
That is approaching to 0.
Yes, it is 0. It is 0. You see, the right hand limit of f of x as x goes to 0 plus, so the right hand limit is 0. And as you say, I agree with you that we cannot consider the left hand limit because our function is not defined. From the other hand, you see, your function due to the definition is defined for x equals 0, and by this definition you have that this function is exactly 0. So as for the third question, I think there is no problem.
But
Agree? Yeah.
there is limit or not?
You
In
have
conclusion, is the
Stop.
function
Valentina,
has
you have
limit?
stop. You have no limit, but you have the right hand limit. You see, here is the difference. You have no limit,
Okay.
but you have the right hand limit, and you have also the value of your function f at this point 0. Agree?
Yeah, agree.
So now the last question. So we want to find, you see, the left hand limit of our function as x goes to 2, and also the value. We have to know the value of my function f of 2. So if we consider our graph, the graph of our function, you see, as for the second question, in this fourth question, you see the function f is not defined for x equals 2. Agree?
Yes, now it's clear.
So from the other hand, you see, if we approach our point 2 from the left, you see, then the left hand side or left hand limit of my function as x goes to 2 from the left will be 1. Here you have your your point x equals 2 and the value of this function at the point, the value of this function at the point y equals 1. Agree?
Yes, Professor.
Yes, I agree.
So, you see, we have the answer for our equation number 4. So the left-hand side limit we can calculate. The right-hand limit. Can we calculate the right-hand limit? What do you think about?
No.
No, because our function is not defined.
Yeah.
Yes? So the same thing is for the value of f at the point 2. This value is not defined, so we can say that is such that f of 2 is not defined. Agree? Question? Or it's clear?
Oh, it's
Yes,
clear.
it's clear.
Clear.
In conclusion, in the point 1, 0, and 2, there aren't limits. Yeah.
You see, Valentina. First of all, where is the trick in this exercise? As for the point 0, for the point 0, you see the graph. Okay? So one thing you can say here that the limit, the right hand limit exists, okay? But there is no limit because we do not know the left hand limit. And the third thing, we know the value of our function at the point x equals 0. Agree?
Yes, I agree.
So the second point is x equals 1. So as for this point, first of all, we can find the left hand limit and the right hand limit. And these limits are different. So the conclusion is we have no limit of our function at x equals 1. And from the other hand, we know the value of this function for x equals 1. It's here. So it is 1. Clear?
Yeah, it is clear.
Finally, Valentina, for you. If we take the point x equals 2, you can find the limit of your function, the left hand limit of your function. It will be 1. You cannot find the right hand limit of your function at x equals 2 because your function is not defined for x greater than 2. And finally, in addition, bad news that even for this point x equals 2, your function is not defined. Here is our general conclusion as for this function, as for this graph. Agree? Is it clear?
Yeah, it's clear.
Very good. So now we pass to the last example as for these one-sided limits. Here you have a rather specific function. So you see the definition. It is the function like this. Between 0 and 2, where the points 0 and 2 are included. But we say that as for the point x equals 1, this point is excluded. And for the point x equals 1, we have that our function is 1. You see, I say it is rather specific function, and I will show you the graph of this function. So you see everywhere between 0 and 2, and these points are included. My function is given by this parabola. But as for the function x equals 1, by the definition of my function, I have that my function is 1. Is it clear, the graph?
Yeah, it's clear.
Clear.
Yes, it's clear.
Now, clear. Now, you see, we have 4 simple questions. We have the first question is the left hand limit. The second question is the right hand limit, you see, and the third is the limit as x goes to 1, the usual limit, not the one-sided limit. So you see, as for the left hand limit, I will go to this point 1 from the left. Evidently, from this graph, we can see that the limit from the left hand limit will be 0. Yes? The left hand limit of f of x as x goes to 1 minus 0 will be 0. Agree?
Yeah, agree.
Agree. So if you take the right hand limit as x goes to 1 plus 0, the right hand limit, you will also have that your limit is 0. Agree?
Yes.
So this means, you see, this means, maybe it's strange, but this means that the limit, the usual limit at the point x equals 0 is 0. Because you have your left hand and your right hand limits, and these limits coincide. They are equal. So your first question, your second question, and your third question, if you want, is 0. The left hand limit is 0, the right hand limit is 0, and the usual limit as x goes to 1 is also 0. Agree?
Yes, agree.
Agree. Very good. Finally, the fourth question is the value of my function f at the point 1. As for this question, there is no doubt because we know that by the definition as x equals 1, we have 1. So from one hand, you see, from one hand, you have that the limit of your function at 1 is 0. From the other hand, by the initial definition of your function, it is 1. So it is possible, you will see in your lectures, that finally we can redefine our function by the continuity. So we can forget about this special point 1 and define our function f of x by 0 at the point 1. But now it's only blah, blah, blah. So is it clear as for this exercise?
Yes, it's clear.
Valentina, really?
Yeah, really clear.
Thank you. Very good. Now, here, I want to propose you. It is not really some questions, but it is a very, very famous. They are very famous questions as for the examination of for the Russian students. So, for your information, you see, you have something. For example, number 1, we have that the limit as x goes to x minus 0, so the limit from the left of my function f of x is a. And the question is how to write this formula in by the quantifiers. So here you can see that there is the solution, or I don't know how to say. We say that in terms of epsilon delta, for any epsilon, we can find delta which depends on this epsilon, such that from our dilated neighborhood, you see here, a dilated neighborhood, because here I write that my difference between x0 and x have to be strictly positive, because our function is not defined. Maybe it is not. If it is continuous, it is defined. But you see from the previous example, we have some problems at this point x0 because the previous function was not a continuous one. So I have to write strictly greater than 0. And if we have this, then the absolute value between f of x and a is the limit, is less than epsilon. Is it clear? Hmm? Eric, is it clear?
So only we need to rewrite with a in the definition of left hand
Limit.
limit. Yeah.
So it is not a problem with A. The only problem, you see, Valentina, in fact, if you want, here, you
Yeah.
see, there is no absolute value. There is no absolute value. Why? Because if we take the limit from the left, then all of the x are less than x0. So the difference x0 minus x is positive. You see? So we do not need the absolute value of this difference, like in like in the usual limit. Because in the usual limit we have to write absolute value of x0 minus x is strictly positive and less than delta. You
Yeah.
see?
Yeah.
So
Yeah.
here, as for the left hand limit, we do not need this because we cannot take x which are greater than this x0. So no problem here. Yeah,
Yeah. I got it. Yeah.
thank you. So the second situation, you see here, I change a little my notation, but you see here we have no problem. We have that the limit as the right hand limit, x goes to x0 plus 0, you see? And this limit is infinity. The limit is infinity. You see, Valentina, in this case, we can consider two different situations. That is, maybe my infinity is plus infinity. Maybe my infinity is minus infinity. I do not know. I write only this, that this limit is infinity. You understand?
Yes. It's clear.
So, for example, you see, if you take the function f equals 1 over x, if x is positive, then my function goes to plus infinity. If x is negative, then my function goes to minus infinity. But if I take the function, for example, minus 1 over x, then you have a different situation. So, as for the mathematics, it is useful from time to time to use only infinity, but we do not precise which is this infinity, plus or minus. Understand?
Yeah.
So, as for this question, I write that for any m, capital M, positive, we can find delta which depends of m, also positive. You see, I replace here my epsilon by some capital M because maybe it is more clear when your function goes to infinity to write not epsilon, which is usually used for rather small numbers. You see, here I want to change my notation and I make use of this capital M. Then, as for the right hand limit, I write that x minus x0 is between 0 and delta, but you see, we say that the absolute value of x is greater than m. In this case, you can imagine your function 1 over x. Then we include in this definition two situations, negative and positive. So I have to write that the absolute value of my 1 over x is very, very great. Very, very great. You see, this is why I make use of the absolute value. Because here in this definition, I write only infinity. Is it clear?
It's clear.
Eric, is
Yes,
clear?
yes, it's clear.
Good. So now, the third question, x goes to minus infinity, and the limit of x is plus infinity. You see the definition. Or, excuse me, how we can write this in the quantifiers. So I take any capital M positive, and here you see as for the infinite intervals, I take another notation. I take capital delta. So there exists capital delta, which depends on m, such that, you see, if x is less than minus delta, then f of x is greater than m. You see, in this limit, f of x goes to plus infinity. So it will be positive and very, very great. But my x is negative because x goes to minus infinity. So I write x is less than minus capital delta. Is it clear?
Yes.
Really, positive. Finally, the last question is lim of x as x goes to infinity is minus infinity. In this case, infinity, if we do not precise x goes to plus infinity or minus infinity, I don't know, because this means in some way that the absolute value of my x goes to infinity, to plus infinity. The absolute value of x goes to plus infinity. X, it can go to plus or minus infinity, but its absolute value goes to plus infinity. So I write, for any m positive, there exists capital delta as in the previous case, such that for any x, you see, here I write the absolute value of x because we do not know plus or minus infinity we are considering. And then the conclusion is f of x is less than minus capital M because we are looking for the limit which is minus infinity. Is it clear?
Yes, it's clear.
Clear. So as for these examples, I think it will be good if you will know this for examination. Because now you see during the lesson maybe it is not very easy, but at home. Okay?
Yes, Professor.
Okay.
Yes, understood.
So now You see, in the previous exercises, we used the definition of the limit, the Cauchy definition of the limit, but it is very hard to use this definition in the practical exercises. So the following theorem, I hope you know this theorem from your lectures. You have the arithmetic properties of the limit. So if you have two functions defined somewhere, domain or a set of real numbers, capital D, and you have a real constant C, and you know that the limit of your function f as x goes to p is L, and of the function g is m. Then four main rules. You have that the limit as x goes to p of f plus g is L plus m. The limit of the product is the product of the limits. If we take a product of a constant of a real constant, your function will be a constant multiplied by the limit. Finally, if your function g in the neighborhood of the limit is different from 0, and moreover, this limit is not 0, then you have that the limit of f over g is the fraction L over m. So four main rules. We will see that in some situations there is the fourth rule is more complicated, if you want, because it is possible that f of p, for example, is 0, g of p is also 0, but we can find the limit. But now we have to use mainly these four rules for the moment. In our future work, we will see another exercises, another examples, you see. So the first exercise here for you, I try to explain all the rules from the theorem. So let us consider the function f of x, which is x squared plus 2x minus 3 over x plus 7, and I want to find the limit of this function as x goes to minus 2. You see, this function is defined everywhere on the real axis except the point minus 7, where the denominator of the fraction is 0. I hope it's clear. So for all other real numbers, for real x, our function is well defined. Agree?
Yes, yeah.
Agree. So you see, if I see the rule number D here in this rule, I say that if the denominator is not 0, g of x is not 0 in some neighborhood of our point -2, then I can use this formula. So the limit of the fraction will be the limit of the denominator divided by the limit of numerator divided by the limit of denominator. You see, -2, we can have a neighborhood of this point -2 where our function x plus 7 is non-zero, is not zero. Agree? Not for all the x. For -7, this limit or this function can be zero, but the near -2, the denominator is not zero. Agree? You can find a
Yeah, I
neighborhood
agree.
like this. You see, you cannot take the neighborhood, for example, -7,0 or -8,0. No. But if you take something like -2.5 -1.5, then in this neighborhood, your function is not zero, it's different from zero. So you can use this rule number D. So I write the limit of numerator, and the limit of denominator. Then using the rule, the second rule, as for the sum, you see, I write that the limit of my function x squared plus 2x minus 3 is the sum of three limits. Same thing in the denominator. Here in the denominator we have no problems. Because we know that the limit as x goes to -2 of x is -2, and the limit of a constant sequence, of a constant function, excuse me, will be this function, so 7. As for the numerator, you see the only one problem here is the limit as x goes to -2 of x squared. In this case, you have to use the second rule of the limit theorem, because x squared is x by x times x. So the final limit after the arithmetic calculus, you have that it will be -3/5. Is it clear the use of the theorem in general?
Yes, it's clear.
Clear. Thank you.
Yeah, it's clear.
So now, good. So now we will try to find some other limits which are not so easy, but they are very easy. But for the moment, it will be something like the sequence of real numbers. You have the function, this function, x squared plus 6x plus 5 over x plus 1. Your function has a problem as x is -1, because at this point, this function is not defined. Agree? We cannot divide by 0.
Yeah, agree.
So we will see. I write here that it is an undeterminate form like 0 by 0, but it is not very clear why it is 0 by 0. So for the moment, we cannot apply the point D of our limit theorem. So as for the sequences, we have to simplify our function, and we can do it very easily. So we can find that x squared plus 6x plus 5 is a product of x plus 1 and x plus 5. You can check it. Then you have x plus 1 in the numerator and x plus 1 in the denominator. So your fraction will be x plus 5. Agree?
Yes, I agree.
So the only thing now, as for the limit of our initial function, is to find the limit of x plus 5 as x goes to -1. So it will be 4. Questions? No questions, I hope. Agree?
Yes, everything's understandable.
Yes. Right.
Good. Now the second example, exactly the same thing. You see, I have a function square root of x minus 2 over x minus 6. So in this case, we have as in the previous exercise indeterminate form by 0 over 0, but we want to find the limit as x goes to 6. So exactly the limit at this point where our function is not defined, is not well defined. You see? So as in the previous example, we have to rearrange, to simplify our function, our fraction. So as usually, as for the numbers, you see, I have in the numerator something like a minus b. So in this case, as usually, I multiply by a plus b and I divide by a plus b. You see this? Agree? Then in the numerator, a minus b multiplied by a plus b is a square minus b square. Agree?
Yeah, agree.
Agree. So now I have following fraction, you see, and I turn my page. So it will be x minus 6 over x minus 6 multiplied by square root of x minus 2 plus 2. So finally we reduce our fraction, and we have that our initial function f of x is exactly 1 over square root of x minus 2 plus 2. The formula number 2.1. Now we have no problems. We have this function is well defined. We have no problem. So the limit as x goes to 6 of my function f is exactly 1 over 4. Agree?
Yes.
Yeah, I agree.
Agree. Very good. Up. So, one example plus, and then we will have a break. Okay? So now, the next example is, as usually, the form 0 by 0. In this case, you have a function which is x over cubic root of 1 plus x minus 1, and we want to find the limit as x goes to 0. In this case, it is the same situation because we want to make use of the formula 2.2. So a cubed minus b cubed is a minus b multiplied by a square plus ab plus b square. Do you know this formula? You know, no problem. So if we take a cubic root of 1 plus x and b equals 1, then I rewrite my function multiplying by a square, ab, and b square, and dividing by the same thing. You see? Now I want to use my formula 2.2 in the denominator. That is here. Oh, no, it's not good. Here. No, it's not possible. So in the denominator, what do we have? We have that in the numerator, we have x multiplied by cubic root of 1 plus x squared plus cubic root of 1 plus x plus 1 divided by 1 plus x minus 1. That is x. Agree?
Yes, I agree.
So simplifying our fraction, reducing by x, we will have that we can represent our function by the right-hand side of the formula 2.3. Okay? That is, if we want now, we can apply our theorem, our limit theorem. So the limit as x goes to 0 of f of x is exactly the limit of this guy, of this sum. So if you take x goes x0, you will have, finally, you will have 3. Is it clear?
Yes.
Good.
Yes, it's clear.
So we will have a break 10 minutes and then I hope we will finish in 45 minutes. Okay? See you.
Okay,
in 10
sounds good.
minutes. Mhm.
Okay, see you.